Hello and welcome to this first class in my course on integration theory. So we're going to go through chapter 1.1 and 1.2, or section rather, in this book. And as I said in my introductory lecture, the problem with integrating more difficult functions is we need to find a way of giving a meaningful number to the size of intricate sets. And also, here's another thing which I forgot to mention, why it's very important to leave Riemann integration theory and move into the integral we teach here is called the Lebesgue integral. Okay, so in the physical world or in Riemann integration theory, you often deal with functions on 1, 2, or 3 variables. So you deal with functions on the space R n, yeah, or let's say R3. This is a huge limitation. So you can, in more advanced mathematics and physics and other branches, probability, you naturally get functions in all sorts of abstract spaces, which we're going to call X. You get functions on these sets, yeah, and you want to integrate them as well. So, for example, in probability theory, if you have stochastic processes, so you think of just a machine giving some output, a continuous signal, and you want to say what's the probability that at some point in time t, the signal is above 15, what do I know? Now you have to introduce measures on sets X, where each element of X is a function. So on function spaces, you want to integrate functions on function spaces. There's a function whose X value, so f of X, where X is another function. Okay, so we need to decide what can be measured. And even in R3, we have this paradox called the Bananski Paradox, which says that if you want to measure all possible sets, all subsets of R3, then you get to contradictions, at least if we want this measure to have some sort of intuitive meaning. So what we usually try to mimic is the notion of size or volume, right? So if you have a small set like a P, you disassemble it into a finite number of subsets and you reassemble them in some other constellation, you want that size to be constant. Well, this is impossible if you want to have a measure on, want to be able to measure all possible sets. So before we talk about how to measure things, measure the size, we need to talk about which sets can be measured. And that has the exotic name, sigma algebras. So this is chapter 1.1 in the book. So basically you can think of sigma algebras as collections of measurable sets. Okay, so we have our basic set X. So X now, it's just any set, right? The power set of X, P of X. Okay, so this is just notation. That is, in fact, a sigma algebra, but as I just said, we don't want that one because that's the one that leads to contradiction. So this is mainly just introducing notation. So we need to put some restriction on, so we want a subset of the power set, right? And we need some restriction on what sort of subsets of the power set we allow. Okay, so then here it comes. Definition. A subset P of X. So this is subset notation. Some authors use this to include that it could be equal, but I don't use that. Yeah, all right. Changed my mind. The book uses this, so I will try to remember to use the same notation. Okay, so if it's not, doesn't have this line, it should be interpreted as a strict subset. Anyways, is called a sigma algebra if, and now we have three conditions that need to be fulfilled. A, X is in the sigma algebra, and the sigma algebra, so this A, from now on going to look like this. Okay, so they use some sort of funny twisted font for sigma algebras, or sets of subsets of X, so subsets of the power set. Okay, so this is the letter A from now on. Okay, so the full space X should be inside. So this will be a member of B. If a set A is in curly A, then also its complement is in curly A, or the sigma algebra. Okay, so A, C means complement, all the points in X which are not in A. And finally C, and this is the important one. If A1, A2, A3, and so on, dot, 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 infinitely many, are all sets in A, curly A, then it follows that the union of all of these sets is also in curly A. Okay, so rather strange definition. One needs to go kind of far into the theory to understand why it's built like this. In the book, there's a fourth condition, but that should be actually a proposition. Okay, so they also want D. If you have exactly the same situation, then it also follows that the infinite intersection, k goes from 1 to infinity, of AK is in A. All right? But this actually, this last condition actually follows from these three. So it's more elegant to have it as a consequence to minimize the amount of assumptions you do. And as a small exercise, let's just prove that. So it's important to get into the mindset of thinking about sets and their operations. So if I take the infinite intersection of a bunch of sets, let me paint it here, it's a bit hard. I'm out of space a bit. So the intersection of these three sets, A1, A2, A3, let's call them, is this guy here. So let's call them A1, A2, and A3. Okay, if I, okay, now consider A1, for example. You take the complement of that, that's everything outside. So we'll have this piece and this piece of A2 and here of A3, right? But it will not have this little piece inside, nor anything of what's inside A1. But then you take what's outside of A3 and you will get this piece. You take what's outside of A2 and you get also this piece. So if you take the union of what's outside of these sets, the complement, you get basically everything except what's here in the middle. All right? So we have formulas like this. So this is the full set minus the union. K goes from 1 to infinity, AK complement. So these are nice exercises to sit around and think about, okay, how would I prove that properly? Because clearly me painting a picture here with three sets is not a mathematical proof. But yeah, I'll leave that up to you and we can discuss it when we meet on Zoom. Okay, so if we believe in this identity, then, and let's say we have a set curly A, which satisfies A, B, and C, but we're uncertain about D, then what we can do is, okay, we look here, AK is in curly A, therefore AK, the complement, is in curly A by B. So all of these sets will be in curly A. Now I'm allowed to take a union, infinite union, by C, right? Which means that this whole thing here will be in curly A. And finally, basically X set minus this set, that's just taking another complement, right? So by this rule B again, we see that this fellow is in curly A. And naturally, I also need to know that X is in curly A, which was A. So I used A, B, C to establish that D follows naturally from these three. Why are these three chosen like that? Well, there's no really intuitive reason. So some of these guys, Lebesgue, sat down, thought hard about it, and came up with these three conditions for what we want, what we need to have something to work with properly. An interesting analogy here is topology, if you had a course in topology. So it's a very similar construction, and they were interested in what constitutes a continuous function. So let me erase here and say that, okay, if we have a set T, which is also a subset of the power set of X, then it is a topology if X should be in T to X1 dot 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 up to Xn. If we have a finite amount of sets in T, then also their intersection. Right? And third, this one is a bit tricky. So, I mean, you see the analogy here, right? So we have D, that's number 2 here. This one and this one is the same. So, okay, you don't want to take complements when we do topology, but you do want to also be able to take unions. The thing here is that we don't want to satisfy with just countable things. We want to take any unions. So what could be, let's say you have a collection of sets, X alpha, where alpha is just some index in whatever possible set. Let me call it A. And if all these, so if this is a subset of T, then you want the infinite or uncountable union to also be in T. Here one has to be careful. So this is a set of sets, so it's a subset of T, but here I do the union of all of these guys and I get a member of T then. All right, so a key difference here is the countability. Here you deal with countable sums or countable unions and countable intersections. Here you have finite intersections and uncountable unions, possibly also, of course, countable unions. So why is it called the sigma algebra here? Sigma, S in Greek alphabet, in German, summing is Summe. So it comes from there, apparently. Yeah. Not so interesting anecdote, but that's the way it is. Okay, so now we know what the sigma algebra is. It wasn't very informative, but to go ahead, let's now assume that A is a sigma algebra. A is always a sigma algebra on X. So unless we work with the real line, which we're going to do from now on, then A is a sigma algebra on X, and I will even forget to mention that most of the time. Okay, so to get closer to how can we integrate here, let's start with something simple, right? So if we have a function which is like a step function on the real line, so if real line is equal to X, then I can call this first set, the interval between this point and that point, A1. The second set, I can call it A2, this one A3, and this one A4. And then they have different heights, H1, H2, H3, and H4. This is the height of the respective box. Yes, now we're back to my introductory lecture. So if this is my function f, I can write f as a sum. In this case, k goes from 1 to 4, hk, a characteristic function of ak. What is the integral of f? dx. It is equal to the sum, k goes from 1 to 4, hk, and then size of ak. That in quotation marks. So the idea of the Lebesgue integral is exactly to imitate this. The only two problems we have here now is that we have to decide which sigma algebra we're actually going to use and how to define size. Yeah. So far we have no good, not even one example of a sigma algebra except the power set. So, do we have any meaningful examples of a sigma algebra? Well, let's at least try to find one on the real line. But even that turns out to be a bit complicated. So, here comes a proposition which will establish the existence of meaningful sigma algebras on the real line. So, proposition, let f be a member of the power set of X, so a collection of subsets, nothing else. All right, so I did a misprint. I had to redo it, so this cuts it a bit shorter. Proposition, let f be a subset of the power set of X, which means that f is just a collection of subsets of X, okay? Then there exists a unique smallest sigma algebra, which we're going to denote sigma of f that contains f. So this is a sort of existence result that makes it meaningful to talk. I mean, now it could, f in the future or later will be like a collection of sets we're interested in. So do we have some sigma algebra which contain those sets? Well, this proposition tells you that, yeah, there is the smallest one and it exists. Because in mathematics, you cannot just assume that things exist without proving them, right? But yeah, these proofs are a bit counterintuitive. It's not like you really build something. So let's look at this proof. I introduced this symbol here, which I'm going to call M, although it doesn't look like an M. This is the collection of all sigma algebras containing F. But I don't know that there are any such sigma algebras. Well, actually, there is one. The power set itself. That's a sigma algebra, and it contains all subsets, so it will contain the subsets in F. So power set of X is an element now of this M. So M is not empty. Okay, and now how are we going to define our sigma algebra curly A? I'm going to define that as the infinite, or countably infinite probably, intersection all possible sigma algebras that contain F. Okay, so what does this mean? Here's an intersection sign, right? So this goes back to basic set theory. There is a bit of material in the appendix to read about it. So if you have a collection of sets, even if it's uncountable many, you can take the uncountable intersection. This just means the collection of sets, let's call them P. So a member is, P is in this if it exists in every possible set B, which is in M. All right. Okay, so since this exists, this infinite intersection will exist. It is something. And does it have any sets? Well, all the sets in F are members of each B, so they're naturally then going to be members here, which means that F is actually a subset of A. All right, so then now it only remains to prove that this new object here, A, is a sigma algebra. So we need to check first that X is in A, but that's kind of trivial because X is in all sigma algebras. M is collections of sigma algebras, so each X will be in each B, so therefore it's also in the infinite intersection.
So because each B is a sigma algebra, so X is in B for all B in M.
Okay, and then now next one we need to prove is that if A is in A, we want to show that the complement here is in A. So you will see that the difficult thing with these proofs is not the details of the proof, it's just coming up with an idea that's so far-fetched of doing. So if A is in curly A, it means that A is in B for all B that we consider, okay? And each B is a sigma algebra. This means that the complement will be in B for all B. And hence the complement is in all of the B's. It's also in the infinite intersection of all B's, which is what we have defined to be A. So it follows that, sorry, the complement is in A, which was to be proven. And then the C condition, which was the countable union. If you have a countable set of sets in A, you want to check that the countable union is in there. It goes through exactly the same way. So then your sequence of sets will be in all of the B's. All of the B's are sigma algebras. You're allowed to take infinite union there and without leaving, and then yeah, yada yada. So I'll leave you to read the details of that in the book. Okay, so the point with that proposition was just to establish that sigma algebras do exist. We still have no idea if sigma algebra, like the smallest sigma algebra containing whatever bunch of sets, is any different than just a power set. But we're going to find that out in a little while. Not this lecture though. But at least going back to the real line, which is our key interest, or best example, let's say, to start integrating on. This allows us to introduce now the first non-trivial sigma algebra, which is called the Borel sigma algebra. Is the sigma algebra generated by, so the previous proposition say there exists a sigma algebra, a smallest one containing all sets of a given. So we're going to say that those sets that we specify generate the sigma algebra. So generated by all open sets in R. Okay, so in this example, F is equal to all open sets. Yeah, so it's a subset of the power set of R. And as such, it generates a smallest sigma algebra containing these sets, and that we're gonna call the Borel sigma algebra. So it gets its own curly letter B of R. Yeah, as I said, we still don't know if this is any different than just the power set, but it will turn out quite soon that it is not. Okay, now we come to the other problem I left open a while ago, is how do you determine size or give a meaningful number to size? Yeah, so this concludes 1.1 in the book. Now we go to 1.2. So we have to introduce now measures. Woo! How to measure size on B of R or any other sigma algebra for that matter. Well, so let's put a new headline here, measures. So since we're dealing with any space X and any sigma algebra A in full generality, I'm also going to introduce measures in this full generality. So definition, given X sigma algebra A, where it's implicitly understood that X is now a set, sigma algebra A is on X, right? A measure is a function which we're going to call mu. So I realize I can't speak to the blackboard and write at the same time the way I would do in a real class. So I'll just write things up and then I'll talk. Given any space set X, a sigma algebra A on X, we now wanted to say what's the size of elements of A, which are subsets of X. Okay, so one subset we have in A is the empty set. So mu, a measure, is a function on A which takes positive values or possibly infinity. Okay, so mu should be able to measure the empty set. Why? Empty set is the complement of X, and complement X is in the sigma algebra, so the complement is in the sigma algebra, which is the empty set. What's the size of the empty sets? Well, it's going to be 0, right? If measures are going to be, this is just stupid. So the fascinating thing is that the only other condition required is the following one. If you have a collection infinitely many sets AK, and I forgot to say that the AKs should then be in A. That was probably implicitly obvious, but anyways, if these are disjoint, then the measure of the infinite union is equal to the sum of the measure of each of the sets, infinite sum. Remember, we're allowed to take infinite unions, countable ones, inside our sigma algebra. So, yeah, a few comments on this definition. Let me put it maybe so you still see it up there. And then plug this one down. Why infinite sums? Why not finite sums? Well, finite sums, you get them for free, but you need also the infinite sums. Remember, we want to take limits at some point in this course. Finite limits aren't that interesting. So what we can do, let's say if you do mu of A1 union A2, you want to know what that is. Well, what you can do then is you just fill out mu of A1, union A2, union the empty set, union the empty set, union dot dot dot. Now you suddenly have an infinite sequence of sets, right? And then you can use number 2 up here to say that this is equal to the infinite sum mu of A. It's just that what does this mean? It means take the measure of A1 plus the measure of A2 plus the measure of A3, which was empty, so that measure is 0, right? So the only two non-zero numbers in this infinite sum is the first and the second, possibly. Therefore, the finite summation rule follows automatically from the infinite summation rule or union rule. Why disjoint? Well, this is very natural to understand. If you have two sets and we somehow want to measure their size and they coincide, overlap on a set, then clearly we don't want to measure this twice, which we would otherwise do, right? Otherwise, if we don't have the disjoint condition, we could even do this. So mu of A, that's the same as mu of A union itself. And then I use this rule up here to get 2 mu of A, which is absurd. So we definitely want to have them disjoint in order to use a formula like this. Okay, so after having introduced sigma algebras, which weren't that concrete, I've now introduced something abstract called measures, which basically had one non-trivial condition, and we still have no good examples. So let's go back to the real line and the Borel sigma algebra. Okay, so for the natural, meaning we want to generalize our notion of distance, of length, right? The natural measure on the Borel sigma algebra, which at least we know about it, it exists and it contains open sets, so in particular open intervals. We want to have that the measure of an open interval, so here the inner parenthesis means open interval from A to B. We want that to be the distance from B to A, okay? This is not a tall order, right? This is kind of, come on, we should be able to do this. And if you have something like a semi-open interval, so going from A up to infinity, you would like that to take infinite. The measure of that should be infinity. Okay, such a measure does exist. It's called the Lebesgue measure, but even the existence of this very basic thing is highly non-trivial. So we're going to get to there, but not really now. One thing I want to highlight is here, this number infinity, which looks like, you know, it's an 8 that fell asleep. It comes into this business all the time, so we have to live with it. We have to accept that this is a number, so to speak, we have to count with. Why? It's because, well, we want to measure any set in our collection of sets. So if we want to give this a finite number, A to B, and we want to work with infinite unions, you can take an infinite unions of sets of length 1, and you get an interval like this. But what length do you want to give that one now? Either then you have to invent like sigma algebras where you cannot take infinite unions, but that's no good. Or if you allow infinite unions, then you also have to allow that some sets are simply infinite. Okay, so from now on, this sleeping 8 is a number we're going to call infinity, and add it to the end of the real line. We also have minus infinity at the end, at the other end of the real line. Okay, so before we get to the Lebesgue measure, okay, I'll write this. So this is introduced in chapter 1.3 and 1.4 because we have to get through some technicalities first. So to end this lecture, we're just going to establish some properties that measures have. So consequences of our very simple definition up here. So proposition, if A is a subset of B, it follows that mu of A is smaller than mu of B. where, of course, A and B are in some sigma algebra on some set X. This gets so tedious to say all the time, so we just assume that for now. Anytime I'm having two sets, they will be in a sigma algebra on some space X. Okay. This is a very natural thing, right? Measuring something that gives a positive number. So if a set gets bigger, the measure should go up. Yeah? How do we prove that? Well, easy. You just note that the measure of B is equal to the measure of A union what is in B, but what is not in A. Okay? And now I can use this summation rule that the measure of a union, a disjoint union, okay? So clearly this one and this one is disjoint by definition of this guy here. So this is mu of B minus A plus mu of A by the second condition of measures. And, well, measures are bigger than or equal to 0, I mean, the number they give. Okay, that's not a condition, that's just like built into it. So here's a positive number, which is big, positive or 0, which means that this number is bigger than or equal to that number. Done. Okay, so here's the first, well, this is a bit of a non-trivial observation still. Very nice. You have a sequence of sets which gets bigger and bigger and bigger, okay? And they are in some sigma algebra where you're measuring units. So now, then you can take the infinite union, okay? Let's take this here. So here is A1, then A2 is a bit bigger, then A3 is even bigger, and then you let this grow, but maybe it doesn't grow. Think of circles with a radius which is just a little bit less than 1, but getting closer and closer to 1. Take the infinite union, you're just getting a circle with an open circle with radius 1. Okay, so the infinite union is something which is well defined. But here we have limit for the first time. So now we need the previous preposition which says, because limits may not exist, so how do I even know that what I wrote here makes sense? Well, by the previous proposition, I know that every time A grows, the measure gets bigger. So here I have a limit of an increasing sequence of numbers. And if you remember your analysis 1 class, this is like one of the axioms of the real number line, that if you have an increasing sequence of numbers, the limit exists. So that's what we're relying on. So the nice thing here is that this limit not only exists, it equals this. How do we prove that? This is a bit more tricky. So to do that, I'm going to introduce new sets. So, of course, A2 was A1 and this ring, but now I'm going to introduce a set B2, which is just that ring and nothing else. Similarly, B3 is going to be the ring between B2, which is inside A3. Yeah, so between the boundary of A3 and the boundary of A2, so to speak. Right? So what's the point here is that the infinite union, okay, so there's the proof. The infinite union of my A case is also equal to A1 union, and then I do the infinite union. K goes now from 2 to infinity of B K, right? Because if I just add the rings all the time, I'm still getting the same thing. And now the B case by construction are disjoint. So technically, okay, what is BK? So what's in AK but not in AK minus 1? That means that these guys are disjoint also from A1. So I can now use my formula 2, the measure of a union of disjoint sets. I can switch that for an infinite sum. Okay. What is actually the meaning of an infinite sum? If you go back to your definition, this is a limit as, let's say, big K goes to infinity of a finite sum, right? But now I can use the finite addition rule. I mean, this guy can go inside here, it doesn't matter. So this gives me limit as K goes to infinity of mu of A1 union, B2 union B3 dot 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 union BK. But now I'm just reversing the process, right? So A1 union B2, that's A2, union B3, that's A3. So here I have nothing but a K in the end, which was to be established. I hate waiting for the blackboard to dry out. No, I'm just going to do it. All right, so the last proposition of today is very similar, but it has a bit of a twist to it. So if now A1 is the biggest one, so they all become smaller, then the infinite intersection of the AKs, you say, now this is also going to be the limit. Well, yes, but there is a catch to it. If A1, the measure of that is less than infinity. Okay, this is actually a necessary condition. An example here, take AK to be equal to the interval from K up to infinity. Then the infinite intersection. So this K is always moving one step further, right? So when you take the infinite intersection, you're actually getting the void set. Whereas now, if we have at least the Lebesgue measure that gives length to something, then we see that the measure of each of these intervals is infinity, but the measure of the infinite union, well, that's void, so it's 0. So clearly this identity here is violated. Proof. All right, so instead of doing the proof, which is actually in the book, I will tell you how not to do the proof. Sometimes that's actually more instructive because the book doesn't tell you how not to do things. And doing things wrong is a really important part of learning to do things right. Yeah, and this is why I recommend against just reading all the proofs, like just take in information without stopping to think first. I very much recommend learning mathematics like this. You see a new statement, you close the book, you think for 1 minute, 5 minutes, up to you, how would I prove this? If you have some idea, then you look in the proof. And then you see if they do the same, good. If they do something different, then the question is, okay, why are they doing it differently? Or what? So this provides much more insight and understanding for what is going on than just saying that, okay, then they did this, and then they did this, and then they did this. You don't learn so much from just feeding yourself with information like that. So let's look now at what would be a very natural approach to this proof and why it will fail. So if you remember the previous proofs, we had A1 was small, and then we got bigger and bigger and bigger, and we worked with these rings, yeah, that you get every time by making it bigger. Here we start with A1 is big and smaller, 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 which also gives us rings that we can work with. Let's paint the picture.
Here is A1, here is A2, oops, A3, A4, and so on.
If I keep on going like this, smaller and smaller and smaller, at some point there will be like a nucleus here, which is the set of points that are in all of these A1, A2, A3, and so on. So this is the intersection. K goes from 1 to infinity, AK. And now we can name the rings B1, B2, B3. So similarly like before, B1 will be A1 set minus A2. So a bit different. Here we go +1 instead of -1 we did in the previous one. So in general, BK will be AK set minus AK plus 1. Okay, so now we get the natural splitting of the set A1 in two pieces, one which is all of the rings, and another one which is the interior here. So one way to express that would be that A1 set minus union of all the rings is the infinite intersection that we are interested in, AK. Okay, and what can we do now? Well, if I do the measure of this, what is that? Well, let me write over here. You remember we had this formula. If A is smaller than B, a subset, then this and this is a disjoint union, disjoint set whose union is B. So we have this identity by the basic addition property of measures. And now, of course, this means that I can move mu of A to the other side. So what do I get here? I get mu of A1 minus mu of the infinite union okay? And this I know it is equal to mu of infinite intersection here of the AK, so the right-hand side. Now, there is a flaw here. I already did the mistake. I don't know if you spotted it, but otherwise, now is the time to go like, where did he? I'm gonna move on because it's still instructive to carry this argument to the end, whether or not for the mistake. So by the previous proposition, this piece here is the limit as big K goes to infinity. Yeah, damn it! Now I made a mistake again. I really understand that some students criticize me for having poorly planned classes. I make just incredible amount of mistakes. I have no idea how I made it to become a mathematician. I should have probably have gone into dry cleaning or something else. But anyways, here I am. This is what I do. So I have to fix up my last blunder. Okay, so if we believe in this identity, then now the B case is a union, it's a sequence of sets which are disjoint. Yeah, so when you have an infinite union of disjoint sets, you can use this basic rule for measures that you can write this as a sum of the measure of each set instead. What is now an infinite sum? Again, well, that's the limit as big K goes to infinity of a finite sum, which looks the same. All right? Okay, so that's just this little piece here. Now let's take all of this together. So you have mu of A1 minus this guy. So then mu of A1 minus the limit of this. It doesn't matter if I put the limit outside. So then I have the limit there, and I can just focus on this expression. But what I have is, well, okay, so this is a finite sum of disjoint sets. So I can think that, well, that will be then the same by the summation rule for measures as the set, which is the union of the B case. And then here I have a minus, which means I do A1 set minus those guys because A1 is sitting outside. So using this formula again. Okay, and then we start thinking, what is this? Well, A1 minus the outer ring B1, well, that's just A2. A1 minus this and this guy, well, that's just A3 and so on. So at the end of the day, we conclude that what we actually have here is mu of AK. This should be a big K. And then the limit is sitting there. So if we put things together, the limit here is equal to this guy, which is precisely what we wanted to establish. Now, in case I haven't already said it, what was the problem here? It is that you're not allowed to do this formula going from here to here. Or in other words, you can't just assume that you can take mu of A and move it to the other side and put a minus like you would do with any sort of normal arithmetic that you've encountered so far. Why? For the simple reason that we have to deal with also the number infinity. So here it could be infinity plus infinity equals to infinity, or 1 plus infinity equals infinity, and that's all fine. 1 plus infinity is still infinity. As long as this plus, we're good with that. But once you get infinity minus infinity, now that means nothing. So we're not allowed to do that. So the fact that measures of sets can be infinite yields limitations to the arithmetic. So you always have to think one step more. It's like, am I doing this just because I'm used to, or at least what in the book allows me to do this step? So here we did this mistake already here, and as we saw in this example, it can really give a problem. Yeah, so the example shows that if A1 has infinite measure, then really you can have on this side infinity and on this side 0. However, the good news now is that once we realize this, the whole proof, how I lined it up, actually works. Because this formula, if B here, unfortunately the roles of A and B are a bit switched here, but B will be the bigger set, right? So if that has finite measure, then this one and this one must also have finite measure, right? For this identity to be true. So then now we have 3 finite numbers. And then of course we're allowed to move one of them to the other side and put a minus. So as long as A1 has a finite measure, this formula is good. And from that point on, I'm just doing calculations. Here I use it again, there's a minus here, but again, if this is finite, all of these guys are gonna be finite numbers. And then I'm allowed to do this arithmetic. The minus goes into a set minus. So an arithmetic minus outside turns into a set minus on the inside, as long as these guys here are subsets of A1. Okay, good. That was the end of today's class, so see you next time.